The purpose of this video is to go through the mechanics of how to apply your inverse trig function formulas for integration. Hopefully in class you've already developed these three formulas that you really need to memorize. So let's just see how we can apply and recognize these formulas. We're going to start off with some easy ones and go to a little bit more complicated ones. So when you're looking at these formulas, you really want to pay attention to, you have a square root, do you have a minus sign, square root, and a minus sign. And then look at the order of that subtraction. We have our constant squared minus our variable. Here we have our variable squared minus our constant. One is sine, one goes with secant. The tangent one kind of stands out on its own. It has a plus sign and it does not have a square root. So looking at this first example, I am thinking tangent. It doesn't look like a u substitution. So if I'm looking at this inverse tangent, I need to identify u squared and a squared. So a squared is 2, so that means a is the square root of 2. U squared then must be 9x squared. So u is 3x, and here comes the key part. You've got to make sure you have that du. So du is 3 dx, or in other words, 1/3 du equals dx. So when you're going and making that substitution, this part right here is 1/3 du. Now you have a squared plus u squared, and that'll integrate into this. So we would have 1/3 times 1 over a. What was your a? The square root of 2 times the arctan of u over a plus c. So we'd have 1 over 3 square root of 2 arctan of 3x over the square root of 2 plus c. So again, identify your variables, your constants, and don't forget to figure out if you have du. Looking at the second example, I see a square root and I see a squared minus u squared, so I'm going to be thinking arcsine. So a squared is 25, a is 5, u squared is 36x squared. You don't put in the negative, that's really part of the formula, if you will. So u is 6x, so du is 6 dx. So again, I have to make my substitution for dx, so dividing by 6. So now this integral is in the format, what takes the place of 1 dx is 1/6 du. I have the square root of a squared minus u squared. And again, looking at my formula, that would be my 1/6 because of my constant times the arcsine of u over a plus c. Going back in terms of x, that would be 1/6 times the arcsine of 6x over 5 u over a plus c. Keeping in mind that arcsine is the only one that doesn't have that 1 over a in front. So again, we're starting out with some easy ones that just kind of follow the formulas. Okay, looking at the next one, well, we have a square root, but this time we have our variable squared minus our constant squared, and we've got something outside the front. So I'm thinking arcsecant. So looking at my formula, this really does look like arcsecant. So again, I need to identify my a squareds and u squares. So a squared is 9, so a is 3, u squared is 4x squared, u is 2x, so du is going to be 2 dx. Now what we have to be really careful here is that this is u out in front. Do I have that? Not really. U is 2x. So I have to solve for x. What is x equal to? X is equal to 1/2 u, and on this one I have to say 1/2 du equals to dx. So let's see if I can get this into the right format. So what is dx equal to? It's equal to 1/2 du. Then what is x equal to? Well, x is equal to 1/2 u. So 1/2 u. Then I have the square root of u squared minus a squared. Now this is really weird, but I'm dividing by 1/2, I am multiplying by 1/2. Those actually reduce to 1. So I now have the exact formula of my arcsecant. So this is going to equal to 1 over a. Let me go back and find a. So that's 1 over 3 times the arcsecant of the absolute value of u, which was 2x, divided by a plus c. So this one was a little bit more complicated. You've got to make sure it fits that formula exactly. Let's look at some more problems just to practice. On this next example, I see a plus. It looks like some squares, so I'm thinking arctangent. So u squared must be, is it x squared? No, I have x to the 4th. So that means u must be x squared. Then du is 2x dx. Oh, that's good because I have that x dx up in top. I can solve for that. I know my a squared is 16 and a is 4. So rewriting this in terms of u, I have 1/2 du divided by u squared plus a squared. So the 1/2, because of this constant, multiplied by 1 over a times the arctangent of u over a plus c. So that's 1/8 arctan x squared over 4 plus c. Well, this next one, double square roots, that just looks really strange. And I'm thinking, well, I got to look under here, and that's my constant minus my variable, and that looks like arcsine, but this variable out in front kind of looks like arcsecant. But either way, I need to, if I think I'm going to either one of those, I still need to identify a and u. So I still think this is in the form of a squared minus u squared. So if a squared is 1, a is 1. So u squared, well, is just x. It's not a perfect square. All right, let's just go with that. So u is the square root of x. So there's a u out in front here. That really looks like arcsecant, doesn't it? But not exactly, because it's not u squared minus a squared. That subtraction does make a difference. But let's go this one more step. We've got to have du. What's the derivative of the square root of x? It's 1 over 2 times the square root of x dx. It's just your power rule. All right, bringing the half down, subtracting it, making it a square root, all of that. That almost looks good because I have dx over the square root of x. That matches. So I've just got to take that 2. So what is this really in the format of? It's in the format of 2 du, again dx over the square root of x is equal to that, divided by the square root of a squared minus u squared. That's really the arcsine. So we'd have the 2 because it's there, the arcsine of u over a plus c. So this is going to be 2 times the arcsine of u. What was u? The square root of x over a plus c. And of course you really don't need to write that 1. We could just put it like that, a little bit prettier. Now this next one, you're going, well, I see something variable minus 1 under a square root. That kind of looks like arcsine, maybe, if it's in the form of u squared minus a squared. So let's just dive in. So if u squared is e to the 2x. Now, if you're thinking, how is that a square? What that really is e to the x squared, because you can multiply those exponents. So that means u is e to the x, but what's du? Du is e to the x. That could be problematic because I don't have an extra e to the x. Well, let's see. What do I do? What do I have? I need to know what dx equals to. So dx is du divided by e to the x. That's just ugly. I need everything in terms of u. Well, if I look up here, u is e to the x. So this could be du over u is dx. Very strange. Alright, so I'm just trying to get what is dx. dx is du over u. So du over u times the square root of u squared minus a squared. And that is arc secant. That is 1 over a times the arc secant of the absolute value of u over a plus c. Now that is really, really different. Let's go ahead and finish it up in terms of our x variable. So 1 over a is still 1. So we'd have the arc secant of the absolute value of u, which is e to the x, over a, which is 1 again, plus c. Very, very tricky. Okay, on this next one we have a definite integral. Always good to practice your trig functions. It looks kind of sweet and innocent, but on the bottom I still see two perfect squares. I have a plus sign. I'm thinking arctan. So a squared is 1. U squared is cosine squared x. So u is the cosine of x. What's the derivative of cosine? Negative sine x dx. And that's almost exactly what I have up here, except for a negative. So I'm going to ignore the definite integral for right now. Let's just write it in terms of u. So I have negative du over a squared plus u squared. So that would be arctan, so that would be negative 1 over a arctan of u over a plus c. But I have to go back and do it in terms of x and with my definite integral. So I'd have negative 1 over 1 times the arctan of u over a, and then I need to evaluate that between pi over 2 and pi. Now isn't that weird? The arctan of the cosine. Alright, so we have negative arctan of, well, the cosine of pi is negative 1. Then we have minus that minus, that's going to be plus the arctan of, what's the cosine of pi over 2? That's 0. Alright, so what is the arctan of negative 1? So the arctan is defined between negative pi over 2 and positive pi over 2. So what angle would give us a tangent value of negative 1? Would be negative pi over 4. Then I have to take care of that negative. So that's positive. Then arctan of 0, what angle gives you a tangent value of 0 is 0. So this would equal to pi over 4. Let's look at this last example. As I look at this, again I have this variable outside. Oh, I've got this natural log of x. Kind of looks like secant, kind of like that other one, except that it's got a squared minus perhaps u squared. So that's really inverse sine. So let's see what happens. So we have a squared is 1, a is 1. U squared is the natural log of x squared. So that's u. So du would be 1 over x dx. Aha! So that is exactly what I have here. Dx over x is du over the square root of a squared minus u squared. That is just arc sine of u over a plus c. Now remember, arc sine's the only one that doesn't have that 1 over a out in front. So let's go back in terms of our x variable. So u is the natural log of x, a is 1, plus c. These are just a few examples of how to integrate with inverse trig functions. The next video talks about more examples using completing the square, which comes up quite often with inverse trig functions.